Okay, do we have everybody? There's Alex and Gabriel. That's all of them. Awesome, everyone's here. Good morning, everybody. I still haven't gotten the screen with the speaker to work, so I have no sound. However, I am still crazy enough to try playing a YouTube video in the middle of class. So you should get sound. I just won't be able to hear it. But it's a video I've seen many times. I know exactly what he's saying. I'll have the closed captions on and all that. We'll see. We'll see how it works. Anyways, we're solving polynomials, right? As I've pointed out, polynomials are this super adaptable, just very generally applicable type of a function. You'll see it a lot in all kinds of different fields. And so being able to understand and solve them is going to be incredibly handy, especially when you get to calculus and the process of using calculus on a polynomial results in you having to solve a slightly simpler polynomial. You don't get out of the solving a polynomial part. So we're practicing secret techniques for solving polynomials. Monday, 2 days thing, right? We looked at Descartes' rule of signs, and this was a quick way to determine not only how many roots there had to be, because we knew how many should have been from the power of the polynomial. That needs to match. Fifth degree polynomial has to have 5 roots. But we could determine how many positive and negative real roots that would show up as actual zeros on the graph just from this little trick. So real quick, I believe you already had access to the answers on here, but let's review those. So take out your work and check it now if you haven't already. So number of possible positive and negative. So 1 and 1, 2 or 0. Remember, you can always decrease by 2. Those 2 zeros being, oh, now they're actually complex roots. Subtracting away there. 2 or 0, 1, 2 or 0, 1, 1, 1, 1, 1. 7 being the most intricate, 5, 3 or 1 or 0. 1 and 1, 1, 9. When you switch to negative, you could have 4, 2 or 0 negative roots. 10 is 3 or 1, 2 or 0. So several combinations thereof. Number 10. And then the second page. Won't read them all out for you. Right, and then that last question, that critical thinking bit, something that has 0 positive real roots. So by default, your function should have all of the same sign on front, right? And then when you're looking for negative roots, you need enough odd powers here that will switch. You got to get at least 5, okay? So the minimum possible power has to be the 5th power. And as luck would have it, the simplest is just 4, 5, 3, 2, 1, 0, all positive, because then the odds all switch and the evens stay positive sign. So you will literally end up with negative, positive, negative, positive, negative, positive, and it will alternate all the way through. You could, of course, bump that up. Maybe you wanted to start at x to the 7th and end at x to the 2nd. That's okay. That would work as well. And of course, the actual coefficients you stick on there don't change that at all. All right, any questions on that sheet? No? All right. Then, for our next trick, we're going to state all the possible rational zeros for a given function. So before we knew how many roots there had to be, we knew how many had to be positive, how many had to be negative of the real roots. Right, so we have some, just to give you an idea here, we had some total number. Right? Some would be complex. The rest would, of course, be real. And one category of real numbers, recall, is rational numbers, numbers that can be written as a ratio, okay? So 2 is a rational number because you could write it as 2 over 1. 3/5 is a rational number, right? Pi is not a rational number. You cannot represent that as a perfect fraction. It's a decimal that goes on forever, okay? So those funky transcendental irrational things. Other irrational would be square root of 2, would be another irrational. Okay, we're not dealing with those. And for the most part, we don't have to deal with those. So we're just looking at the rational ones. And then we had a way to count the number of positive and the number of negative. And now what we're going to be able to do is we're going to be able to generate a short list of the possible roots, the possible zeros. Every rational zero for this polynomial must come from this list of numbers. All right? That's pretty good, seeing as without that you'd be left with, well, it could be anywhere between 1 and infinity, right? Or -1, -infinity. Or anything in between, even less than 1. We're dealing with rationals here. It could be 1/2. You don't know yet. So we're going to generate a short list. It might not always be that short. You could be looking at something like 20 different numbers, but that's a lot better than infinity. Now, what we're using here is called the rational root theorem. Okay? And that says this: all the possible rational roots of a polynomial can be represented as a single fraction p over q, such that p is all the possible factors of the constant, and q is all the possible factors of the leading coefficient. Okay, write this down right here. Factors of the constant divided by factors of the lead coefficient. So, before you can begin using this, just like Descartes' rule of signs, you must first GCF any extra variables out so that you do have an actual constant term. Okay? So this is all of the rational numbers. We're not counting 0 here. That would be factored out independently. But this would give us all of the rest of them. Can be found with this process. And I'm going to give you 3 different examples. I'll scroll through one on this page. I've got a video of someone doing another example, and then I'll do another quick one together with you from the worksheet. So we're going to get 3 whole examples of this guy. Let's take a look. Here is our polynomial. 1, 2, 3, 4 terms. Quadratic. Why did 3x squared minus 4x? I think that was supposed to be a cube. That's a typo there. Good job, site. Oh, you're still writing that down. I'm sorry. Yeah, pretend this is actually a cubic here. Can't trust anybody on the internet. All right. Got it. Let's go. So we've got our polynomial, and it's got to be in standard form as usual, right? GCF out any extra variables so that we do have a constant, and we've got the highest power up in front. And all I care about is what are those numbers, the coefficient here and the constant itself. So the lead coefficient is 3, the constant is 6, as they say right here. And we want to list all possible factors of those numbers, right? So how can you divide a 6 and get no remainder? All factors of 6. 1, 2, 3, 6. That's it. It's a fairly short list, right? And we have to consider both positive and negative. So really, P could be positive and negative 1, 2, 3, or 6. That's our P term, okay? And then our Q goes with the lead coefficient 3. So what are the factors of 3? Positive and negative 1 and 3. And then you'll set up this great big fraction right here. All the P's over all the Q's. And find every combination, every unique number of reducing those fractions, right? So for example, 2 over 1 is 2. 6 over 3 is also 2. We're not going to write down 2 twice, all right? So all the factors of the constant divided by positive and negative 1, you would get 1, 2, 3, 6. And if you divide all those by 3, there's all of them over 3. Reduce 1/3, 2/3, 1, and 2. So notice we have 1 and 2 repeated. So our final list, put together all the possible factors, no repeats, positive and negative of each one. We've got 1/3, 2/3, 1, 2, 3, 6. 6 numbers. Well, actually 12 because you have the positive and the negative of each one. Okay? And so from that list, you can start testing and checking which ones are going to be roots and which ones are not. And there's a few tricks on ways to test those. Of course, you can try factoring one out. You can try dividing them out. You can use the remainder theorem. Okay, so if you just plug these numbers into the function, whichever ones give you 0 as an output, those are your roots, right? So any of those methods will work from there. Maybe some of these you already know from other techniques, maybe using the quadratic technique, you could factor out some of them. And all this helps you narrow down some of the options. And then we can use this, combine this with the rule of signs. If you know only one of them is going to be positive, as soon as you find the positive, let's say, I'm checking the 1. Oh, it's positive 1. You now eliminate the other half of your list. You never have to check another positive number again. You're just going to test all the negative versions until you find the negative roots, right? So that really helps you narrow down your list there. All right, let's see this in action then. Oops, start at the beginning. This guy is a little goofy.
I don't get it! Rational zeros theorem. There's really not much to get, people. But in order to get this example, we first need to get a definition.
The rational zeros theorem. If P over Q is a rational number written in lowest terms, and if P over Q is a 0 of F...
You don't hear? Oh, right. I'm sorry. Zoom with their fancy share screen, share computer sound. There we go. I always forget I have to do this.
I don't get it!
How about now?
Rational zeros theorem. There's really not much to get, people. But in order to get this example, we first need to get a definition.
Yes. Okay.
The rational zeros theorem. If p over q is a rational number written in lowest terms, and if p over q is a zero of f, and a polynomial function with integer coefficients, then p is a factor of the constant term, and q is a factor of the leading term.
Okay.
Okay. Don't bother trying to write that down. I don't like that definition. I prefer using the other site here. This to me is much more straightforward. The other one words it kind of backwards. But just stick with this, all right?
Now that we got that definition out the way, I need to look for my P and my Q. Okay, my P comes from my lagging. My Q comes from my leading. Okay, what do we need to do? We need to break it down. Oh, because the possible divisors for our polynomial, if it's going to divide it even with a rational number, it's going to be the quotient of P over Q. Okay, or the factors of them. So then my P factors, those are going to be 1, 3, 5, and what, 15? Are those all the factors of 15? Yes. My Q factors, my Q. That's going to be 3 and say 1. Those are the factors of my Q. Okay, so what am I going to do? I'm going to go and I'm going to write I'm going to list the factors of P over Q. Why do I want to do this? Yeah, because I want to try to factor this thing using division, because I may not have the skills and techniques to factor it by the traditional methods. So I want to factor by division. So I need possible divisors. And what are they going to be? They're going to be the quotients of P over Q. You're going to say this is an awfully long list, but hey,
and then tomorrow
it's a lot shorter than all the numbers in the entire world.
Division
so let's get at it, people.
Part that he's referring to there.
Okay, so I'm looking for P over Q. Yes. So then why don't I just fix a Q? Sure. Here, I'm going to fix a Q. Let me let Q be 3. So I'm going to take all of these, and I'm going to divide them by 3. So in my list of potential divisors, I'm going to have 1 over 3. I'm going to have 3 over 3. I'm going to have 5 over 3. And I'm going to have 15 over 3. Okay, so now that I've exhausted 3, let me fix my Q now to be 1. The other potential denominator in my rational factors, if there are any. Yeah, now I fixed Q to be 1. So I'm going to take all my P's and divide them by all my Q's. Here we go. That's 1 over 1. That's 3 over 1. That's 5 over 1. That's 15 over 1. Okay, so then your rational zeros theorem said something about reduction. Let's go ahead. Let's reduce these, and if there are any in common, we're going to just take them off our list. So this is 1 over 3. That one's 1. This one's 5 over 3. This one's 5. Okay, so wait, 1's already on my list. Forget about it. 3, is it on my list yet? It's not. So 3 is a potential divisor. And 5, is it? There it is. Don't worry about it. And 15. Okay. So what we just listed is all the potential rational divisors of our original polynomial. And then there's 1, 2, 3, 4, 5, 6, 12 of them. Why? Because in each case, it could be plus or minus, 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 plus or minus.
Love his delivery on that.
Yes. So when you start dividing these, start with the nice ones. Start with 1, then do 3, then do 5. Fractions are fun. Yeah. We just listed all of our potential factors, or zeros, of our polynomial.
Okay. So there you are. And yes, I would recommend, if I can find a good screen, I would follow pretty much this exact process. Okay? Until you get really comfortable with these, I would not skip this list and start trying to reduce things ahead of time. You're going to confuse yourself, especially the longer this gets. Okay, the more things you have to keep track of, go ahead and write those down so you don't lose any of them and you don't accidentally miss any combinations. All right, any questions at this point? No, no, yes. Okay, then let's do one more together, straight from your worksheet. F of x equals 3x squared plus 2x minus 1. I have a power of 2, 1, 0. It is in standard form. Check. My last number on the list has no variables. It's a constant. Check. This is doable, as is. So my constant is my p. So all possible values for p would be every factor of 1, which is just 1. Oh, this one's actually going to be pretty short. And all possible factors of q, that comes from my leading coefficient, so that would be 1 and 3. So then p over q would be, start with the exactly as he did on the video. I would say set one denominator. Okay, put all the p's over 1. Done. Put all the p's over the other denominator. Done. Okay. That's the unreduced set. And go ahead and reduce those numbers. 1 over 1 is 1. 1 over 3 is still 1/3. And it wanted just to state the possible rational zeros. That's it. That's my answer. Okay? Later on, when you get down here, you want to then find all rational zeros. So now you have to test. Say, here's the list of possibilities. I need to check each one. If you don't have the division techniques, if you don't remember synthetic division of polynomials, we'll go over it tomorrow, you can use the remainder theorem that's and draw on the fact that, hey, f of a 0 should give me 0. So we can test these. I can go through and I should be able to say f of 1 should give me 3 times 1 squared plus 2 times 1 minus 1. What do I get? Well, 3 times 1 squared is 3 plus 2 times 1 is 2 minus 1. 3 plus 2 is 5 minus 1 is 4. Oh, I didn't get 0. So this is not one of the roots. Make sense? How about the other one? While we're here, let's test it. Pretend that's not there. I need more room. How about f of 1/3? Is that a root? Should hope so. We're running out of numbers here. F of 3 times 1/3 squared plus 2 times 1/3 minus 1 equals 1/3 squared is 9. 9 times 3 1/9 times 3, so 3/9 is back to 1/3 plus 2/3 minus 1. 1/3 plus 2/3 is 1 whole. Minus 1 equals 0. Yippee, we found one. Hooray! Where'd the other one go? This is a quadratic. I'm supposed to have 2 roots. I only found one. Only 1/3 worked. What'd I do wrong? Uh-oh, guys, I'm missing something. I skipped a step. Yes, thank you, Alex. Plus or minus? He said it enough times in the video. How could you forget? Plus or minus? Plus or minus? Don't forget your plus or minuses. Both versions. So positive 1 did not work. Maybe negative 1 will work. Or maybe negative 1/3 will work. I'm not sure. You'll have to test. Well, okay, I say you'll have to. If you wanted to know, you would have to test it. You are not required to do so for answering this first question. But that is the process that you can, or one process you can use on 9 and 10. Okay, questions? No? You're all set? All right. Then for today's work, just questions 1 through 10. That's it. Stop there, front page, and I already did one for you. You only have 9 questions left. You're welcome. And you have the rest of the period to work.